Okay, so in the previous video, we derived this formula up at the top here for finding the volume of the solid of revolution using cylindrical shells. And remember, the key thing to remember for this is circumference times height times thickness. In this integral, the thickness is always going to be your differential. It's either going to be a dx or a dy, depending on what we're rotating around. The circumference and the height can take slightly different forms than what we see here, depending on what the region looks like. And so it's really important to draw things out when you're doing this type of a problem. So for this first example, this is going to be the most straightforward one. Find the volume of the solid generated by revolving the region bounded by y equals e to the negative x squared, y equals 0, x equals 0, and x equals 1 about the y-axis. Very first thing you want to do, which is the same for all of these problems, is sketch this region out. So if you have taken statistics, you will probably recognize what this curve looks like. You may not recognize it from just looking at the function, but that y equals e to the negative x squared, when you graph it, it makes a bell curve, otherwise known as a normal distribution in statistics. You don't need to know that terminology, but that's what it is. It would have another branch here. It's symmetric about the y-axis because that's an even function. But for the region we're talking about, it's all going to lie within the first quadrant. So here is y equals e to the negative x squared. Let's label that here. Okay, and then we're bounded by y equals 0 and x equals 0. Those are the x and y axes respectively, and the line x equals 1. Let's just assume that's like right here. Okay, so we're looking at this region right there. All right, now what I want to do is put another little mark on here indicating what axis I'm rotating about. So it says the y-axis. To remind myself which axis we're rotating about, I'm going to do that. And remember, the key thing here for the shell method is to draw yourself a little rectangle in your region and make sure that your rectangle is parallel to the axis you're rotating about. So I'm going to put it like right here. Okay? If we were doing the washer method, that rectangle would be perpendicular to that axis, not parallel. But we're looking at a parallel rectangle in this case. And remember, I'm using the midpoint of that rectangle to determine its height. I'm going to just call that value x to keep it general. Okay? So think about if I were to rotate this rectangle around or about the y-axis to create that cylindrical shell, then the distance from x to the y-axis is going to become the radius of that cylindrical shell. So the distance from x to the origin literally is just x. Okay. The height is another thing that we're going to need to identify here. What is the height of this rectangle? Well, it comes from plugging x into our function to get the y-coordinate of this point. And this is what the function is. It's e to the negative x squared. Okay? So if I was going to use this formula here to compute this volume by cylindrical shells, I'm integrating over the interval on the x-axis that I'm defining this region on. So that's from 0 to 1, which I can see in my picture. And then my circumference would be 2 pi x. And in this case, it's not just because it says 2 pi x here, but it's literally because that x represents the radius, right? Circumference of a circle is 2 pi r. And the radius of this thing, if I were to create that cylindrical shell, I can see from the picture would be x. But remember, in different examples, this might change into something slightly different. Next, I need the height of my cylindrical shell, which will be the same as the height of my rectangle. That's e to the negative x squared. And then I have this dx right here. Okay? Which I can slightly simplify this. The 2 pi being a constant can be pulled out. So I'm just going to go ahead and pull it out. This is the integral from 0 to 1 of x e to the negative x squared dx. Okay, this is a classic example of an integral that requires a u substitution. And hopefully you can see that our u should be negative x squared, which means du is going to equal negative 2x dx. Okay, now if I look at what I have here, I have du equals negative 2x dx. Notice I have a 2x dx all in my integrand already. I did pull the 2 out, but you could bring it back in if you wanted to. It still counts as part of your integrand. What's missing is the negative. So I need to multiply both sides of this by a negative 1 to get negative du equals 2x dx. So that means I'm swapping the 2x dx out for a negative du. Let's bring the negative out here. So there's negative pi. And then this becomes e to the u. And then remember, all that's left from what I swapped things out for is du. So e to the u du. Now, what about my limits of integration? Well, we've done an example in a previous section with a u substitution. Remember, you take your limits of integration that are representing x values and plug them in here to get the corresponding u values. If I plug a 0 in here, I clearly get a 0. If I plug a 1 in here, I get negative 1 squared, which is negative 1. Okay, here I can use this minus sign to flip the order of integration. We saw that in the previous section. So now I have negative 1 to 0, e to the u du, and my negative is not there anymore because I used it for something. This is a simple integral. The exponential function is its own derivative, or own antiderivative, and its own derivative. I get pi times e to the u from negative 1 to 0. E to the 0 is equal to 1. And e to the negative 1 is the same thing as 1 over e. So I can write this as minus 1 over e. Or you could leave it as e to the negative 1. Either form is fine. That's going to be our answer. Okay? I think I may have said this before, but I really, really want you to resist the urge to plug this into a calculator. Please don't do that. In calculus, even in algebra, we prefer exact representations of our answers to things. And if you plug this into a calculator, you're going to get a decimal which is approximating the correct answer. Because this is an irrational number, you're going to get a decimal that goes forever and never repeats. So if you're going to cut it off somewhere, you're approximating it. Don't approximate it. Leave it in this form. This is significantly better. All right. So that is probably the simplest example we're going to do in this section. We're going to gradually make these a little bit more difficult as we go. Let's do another one. I want to find the volume of the solid generated by revolving the region bounded by x equals negative 3y squared plus 12y minus 9 and x equals 0 about the x-axis. So we're rotating about a different axis this time. Let's take a look at what the graph of this function would look like. It turns out I only need to draw the first quadrant again. How do you graph this? Well, x equals negative 3y squared plus 12y minus 9. I notice that I can factor a negative 3 out of that, which is going to give me y squared. That plus becomes a minus 12y, and then I'm going to have a, oh no, sorry, not 12, it's minus 4, because I factored a negative 3 out, right? And then plus 3 here. Sorry, that's sloppy. This quadratic here can be factored even further. So I get negative 3 times y minus 1, y minus 3. That's how we can factor this, okay? My purpose behind doing that is because if x is equal to this, I could plug a 0 in for x and get the y-intercepts of this parabola. Because this is a quadratic in the y variable, I know it's going to be a horizontally opening parabola. And I can see that because my leading coefficient is negative, it'll open towards the left. And I also can see that I have y-intercepts at 1 and 3. So we're looking at a parabola that's something like this. And as you've kind of seen over and over again, I am not super concerned with having a perfectly to scale graph. I just want enough information to get the answer correct. So the intercepts here are going to end up being important. But we want the region bounded both by that curve, that parabola, and x equals 0, which is the same thing as the y-axis. So we're looking at this region right here. Okay? Now we're also rotating this region about the x-axis. So we're looking at one of these. Okay? To construct cylindrical shells, remember that what you want to do is draw a rectangle within this region that's parallel, not perpendicular, to the axis you're rotating about. So I'm going to just pick a spot here, and this is what one of those parallel rectangles are going to look like. Okay? Now, what do we need from this rectangle? Well, we want to imagine rotating it about the x-axis to create a cylindrical shell. And we want two things from that shell. We want the radius, because that'll show up in the circumference formula that we need. And then we want the height, okay? So what I'm going to do is label the position or the midpoint of the base of that rectangle as a y. I don't want to call it x because it's going to the y-axis now. It's not going to the x-axis. Let's call that y. What would the radius of this cylindrical shell be? Well, remember, it's just the distance from your rectangle to the axis you're rotating about, which, if I'm calling that y, is exactly y. What about the height of that rectangle? Well, the height is going to be given by our function, because the distance from here to here is simply whatever I get by using the function that bounds this thing on the right. So that's going to be negative 3y squared plus 12y minus 9. Okay, hopefully you can see that that's the distance from x equals 0 to x equals that quadratic. So now I can start putting things together. My volume is going to be the integral. And my limits of integration, remember, now we're looking at our rectangles drawn relative to the y-axis, not vertically relative to the x-axis anymore. So that means that I want to integrate this thing in terms of y. My limits of integration have to live on my y-axis, not on my x-axis. So I'm looking at the interval from 1 to 3 here. 1 to 3. Okay? Now what do I need? Circumference. So remember, that's 2 pi r, where r is my radius, and here we determined that radius would be y, so it's going to look like 2 pi y times the height, which is this term right here, negative 3 y squared plus 12y minus 9, times my thickness, which is always a differential, but again, we're integrating with respect to y here, so I need to write that as dy, not dx. All right, I want to evaluate this integral, and I'm going to try and simplify it a bit. So I can factor a 2 pi out from here, and we've already seen we can factor a negative 3 out from here. We did that right here. So I'm going to factor 2 pi and a negative 3, which is going to give me negative 6 pi altogether. And then the quadratic that I'm left with, which is what's in parentheses here, is being multiplied by a y. So I can distribute that y in to turn this quadratic into y cubed minus 4y squared plus 3y dy. And we are integrating a polynomial. Those are the easiest types of things to integrate, so that should be fairly straightforward. We're looking at this. Negative 6 pi times y to the 4th over 4, that's the first term, minus 4/3 y cubed plus 3 halves y squared, y squared. Okay? And we're going from 1 to 3. Okay? Now, I'm going to, I'll write out the next step, but I want to point something out here. As we kind of progress through this course, when we have integrals that involve a lot of like arithmetic and adding and subtracting fractions and stuff like that, my expectation is that you are only at this level because that stuff should be really old news for you. So I'm going to write some of the steps out here, but as we get further and further through the course, I'm going to leave those steps out of my examples because I'm expecting you to be able to fill in those gaps yourself. It's not really worth our time to do a whole bunch of arithmetic in the lectures, okay? But for just this once, I'm going to do negative 6 pi right there. Plugging a 3 in, I'm going to get 3 to the 4th over 4 minus 4/3 times 3 cubed plus 3/2 times 3 squared minus, plugging a 1 in, I already know what each of these is going to come out to pretty easily, 1/4 minus 4/3 plus 3/2. Put that in parentheses to remember that your minus should distribute. I'm going to go straight to an answer here, but I want to point something out. You notice that I left this in terms of 3 cubed and 3 squared and stuff like that. The reason I'm doing that is because it makes it a little bit more apparent how to cancel things quickly. So instead of plugging this in or working this out in my head, because 3 cubed, I already know that's 27. I'm seeing that there's a 3 down here, which I could cancel and make that a 3 squared. That helps with some mental math if you're trying to do a lot of this in your head, okay? But all that aside, the solution to this after working everything out is going to come out to 70 pi. I encourage you to work that out on your own. Okay, quick sanity check. We're talking about volumes of solids here, which in the context that we're talking about them in this class, those can only come out to be positive numbers. So if I ended up getting a negative number as a result here, that would have clued me in to the fact that I must have done something incorrectly. You should do that for all of the problems in 6.2 and 6.3. Do a quick check and say, is my answer positive or negative? If it comes out negative, where did I go wrong? Okay. Let's end this video here, and we'll try to wrap up our last couple of examples in part 3.